this session, we are going to discuss about the nanometrology. Nanometrology is the science of measurement at the nanoscale level. So, this diagram shows the scale from 1 meter to the 0.1 nanometer, 1 meter, 1 centimeter, 1 millimeter. We are using day-to-day life for measuring length of table, length of computer chip, diameter of the workpiece, diameter of the pin, diameter of the circle. Then I'll come into the micron meter, 10 micron meter for size of animal cell, size of bacteria that can be represented by 1 micron meter, 100 nanometer for size of virus, 10 nanometer represented for size of DNA, then 1 nanometer, 0.1 nanometer. These are the scale represents the meter to nanometer. This table represents the type of nanomaterial and related to the diameter or thickness. Nanocrystals. Crystals are like metals, inorganic material like oxide, nitrates, sulfides, etc., which varies the diameter for 1 to 15 nanomicron. Nanofilms, layers of quantum dots, are made of lead, selenide, indium, arsenide, etc. 1 to 10 nanometer. Nanowires, metals, oxide, nitrates, sulfides, etc. 1 to 10 nanometer. Nanotubes, most of the researchers are doing in nanotubes projects, which varies the 10 to 1 nanometer. Then nanosurface, 1 to 1000 nanometer. The applications of nanomaterials are nanosensor, water purification, lighting, nanocomputer, nanotechnology based garments. Then nanometrology techniques. What all the parameters, what all the properties we can study by using nanometrology techniques are in them. We can get the morphology, that is size, shape of particle, crystallographical information, that is detection of atomic scale defects. In scanning electron microscopy SIM, we can get the topology, topography, morphography, composition, crystallographic information, that is the arrangement of atom. In scanning tunneling microscope, we are getting the three-dimensional surface topology, that is size, shape, roughness, defect, electronic structure. In atomic force microscopy, AFM, or scanning force microscopy, we can get the details of roughness, elasticity of surface, grain size, frictional characteristics, specific molecular interaction, and magnetic features on surface. And the fifth one is X-ray diffraction, that is XRD. From that we can get the crystallographical information like type of crystal structure, film thickness, interface roughness. Now we will see one by one. We have two type of electron microscope. One is transmission electron microscope. Another one is scanning electron microscope. Here we are using electron instead of light, like in optical microscope. In them, it is possible to form a transmission electron diffraction pattern from electrons that have been passed through a thin specimen. If these transmitted electrons are focused, their very short wavelength would allow the specimen to be imaged with a spatial resolution much better than the light optical microscope. That is, we are focusing the large amount of voltage. So voltage is inversely proportional to the wavelength. So we are getting the very short amount of wavelength. From that we are getting the image. From this we are getting only 2D image. In TEM, thing is so this is the specimen. We are passing the electron beam. Some electrons are scattered in terms of augum electrons, secondary electrons, back electrons. Some electrons are scattered. The unscattered electrons are passed through the specimen and from that we are getting the image in fluorescence screen. That is the principle behind the TEM. We are getting the 2D image in TEM. In TEM, electron penetrates a thin specimen. Electron penetrates a thin specimen and are then imaged by appropriate lens, quite similar to optical microscope. In optical microscope, we are using light. In TEM, we are using electrons. One limitation of TEM is that unless the specimen is made very thin, the electrons are strongly scattered the specimen or even absorbed rather than the transmission. So we have to make the specimen very thin. That is the main task. The next one is scanning electron microscope. SEM is a type of electron microscope that produces image of a sample by scanning the surface with focused beam of electron. Thus, electron will interact with atom of the sample and produce the signal that contains the information of the sample. So it is a type of electron microscope. As I told earlier, we have two type of electron microscope. One is STEM, another one is SEM, transmission electron microscope. Another one is scanning electron microscope. So which that produces sample image of sample, but by scanning the surface with the focused beam of electron. This electron interact with the atom of the sample and produce various signals. The purpose of same or we can get topography, morphology, composition, and stratigraphic information we can get. The scanning electron microscope is arguable by most versatile microscope with magnification ranging from 5x to 10 power 6x. It provides excellent resolution, amenable to automation and user friendly. These features have made it most widely used of all electron beam instruments. Sample preparation and examination is quite simple when compared to other techniques. A wide range of nanomaterials starting from powder to films, pallets, wafers, carbon nanotube, and even bit sample can be examined. It is possible to correlate the observation made at nanoscale to microscale and draw reliable conclusions. So these are all the advantage of SIM. And here signal generated in SIM. So as we discussed in the TEM, so electrons are hit on the sample. Some electrons are diffracted, that is backscatter electron, light, auger electrons, secondary electrons, X-rays are diffracted. These are the signal. Scanning electron coil, backscattered electron and secondary electrons plays an important role. Here electron guns which produce the electron. We have condenser lens which focus the electrons towards the specimen. Here the scanning coil is there. This scanning coil absorbs the electrons and backscattered electrons are there which that is reflected, and secondary electrons are there. The images are collected from the three detectors, that is scanning coil detector, backscattered electron detector, and secondary electron detector. From these detectors, signals are amplified and images are scanned, and we can see in the display device. In SIM, we can get the three-dimensional image, whereas TEM we can get two-dimensional image. Next one is scanning tunneling microscope. This is working behind the principle of quantum tunneling. What is meant by quantum tunneling effect? When an atomically sharpened tip under a small voltage is brought closer to the surface of sample, so that the separation is of the order of nanometer. There is a small change in small change in current in the circuit. This effect is called quantum tunneling. That is, here we have a chip and we have a specimen, and high voltage of this caused to this chip. So this gap, nano gap, plays a vital role. From that we are getting the image that can be analyzed later. This induced current is referred as the tunneling current. When the tunneling current increases when the gap between the chip and the sample decreases. So the gap, the nano gap, we are maintaining the nano gap, the tunneling current will high. The change in tunneling current can be calibrated with respect to the change in gap. It also gives the 3D image like a sim. The main purpose is we can get the three-dimensional surface topology like size, shape, roughness, defect, electronic properties of nanostructure. In other words, if we scan the chip over the sample surface while keeping the tunneling current constant, the tip movement depicts the surface topography because the separation between the tip apex and the sample surface is always constant. The next one is atomic force microscope. This microscope differs from other microscope because it does not form an image by focusing light or electron on a surface like optical or electron microscope. In IFM physically feels the sample surface with a short probe, building up a map of height of the sample surface. Like the surface of nest tester, it touches the probe is there, it touches the surface, and based upon the height, it produces the map. By scanning a probe over the sample surface, it builds up a map of height or topography of the surface as it goes along. Moves up and down. Here, laser beam is focused on the cantilever. Cantilever contains tip. This tip moves up and down on the surface of the specimen, and deduction of the beam are captured in the diode. Cantilever moves up and down. The laser oscillates. When cantilever moves up and down, the laser oscillates, and this oscillation informations are captured in the diode, and from that we can get the image for analysis. Next one is X-ray diffraction system, that is XRD. It is an ideal method for examining the sample of metals, polymers, ceramics, semiconductors, thin films, and coating. It can also be employed for forensic and archaeological analysis. A two-dimensional diffraction pattern provides abundant information about the atomic arrangement, microstructure, and defects of solid or liquid material. Here, Bragg's law behind the XRD. Bragg's law describes the relationship between the diffraction pattern and the material structure. If incident rays hits crystal planes with an incident angle theta and reflection angle theta shown in figure, a peak is observed in the graph. When Bragg condition is satisfied, the condition is n lambda equal to 2d sin theta, where lambda is the wavelength, d is the distance between each adjacent crystal planes, theta is the Bragg angle at which one observes a diffraction peak, and n is an integer number called the order of reflection. Here X-ray generator is the X-ray optics. X-ray is coming out through the X-ray optics. Here sample is uh, hold by the sample stage, and from that X-rays are passed through the sample, and here we have sample alignment as monitor is there. From that we can get the detailed analysis. This is the two-dimensional X-ray diffraction system. These are the some reference. In this discussion, we discuss about the what is nanoscience and what all the techniques are used to get the information from this specimen. The techniques are TEM, transmission electron microscope, scanning electron microscope, then AFM, then XRD, etc. Happy learning.